This is the lecture for 7.1. This is one of two parts. Let's get started. We're going to investigate again the relationship of velocity to position, and we're going to do so using this particular velocity equation, t squared minus 8 over 1 or t plus 1 quantity squared. We're going to note that this velocity function crosses the x-axis, or the time axis in this case, at some position A. And it wants to know, well, what's going on with this motion? Well, we're going to say that the motion of the particle is moving to the left while t is less than a, because during that time the velocity is negative. This being zero velocity, this being positive velocity, this being negative velocity. We're going to note that at t equal a, the particle is at rest. It's not moving. The velocity is zero. And lastly, that when t is greater than a, the particle is moving to the right. This has a play in things as we look into the next question, and that is, well, where is this particle at various times? Well, let's start with this idea. We know that the velocity function is given to us, and if we wanted to find the position, we could find it by taking the antiderivative of the velocity equation. The antiderivative of t squared is 1/3 t cubed. The antiderivative of negative 8 times quantity t plus 1 to the negative 2 power is going to be negative 8 times negative 1 times t plus 1 to the negative 1 plus some integrating factor c. Now, how do we find the value of c? Well, we focus in on this initial condition and say, well, given that we have a position equation with a constant, let's plug in what we know. When t is equal to 0, the position is 9, so every place we see t, we replace it with 0, and we set that whole thing equal to 9, and therefore 8 plus c equals 9. Now that means c has to equal 1. And now we have this general equation that we can use for finding out the position given any particular time. We're asked, hey, what is the position at time equal 1? Well, let's take the value 1 and plug it in for t. So every place I see a t, I put a 1, and if I evaluate that, I'm going to get 1/3 plus 8 over 2 plus 1, or 16/3. Likewise, if I want to answer the second question, what is the value of the position at time t equal 5, I can take, and every place I see the t value, I can put in the value 5. Again, I'm going to get something divided by 3, 125 divided by 3, plus 4/3 plus 1. And if we evaluate that, we get 44. Okay, now a couple of things to note here. Please note that 16/3 is less than 9, and that should be okay. 16/3, which is 5 1/3. Well, we started at position 9. We went backward because the particle was moving to the left, got to 16/3, and then over the course of this time, we get bigger than 9 because there's so much area under that curve. Area under that curve, that's an important thing to note. We know that also by using the fundamental theorem of calculus part 2 that we could have thought generally of position as being some initial position plus this integral. This is straight out of our rewriting of fundamental theorem of calculus part 2. We want to find the value of position at the position at time equal 1. Well, it's going to be the position at time equal 0 plus the integral from 0 to 1. We want to find the position at time equal 5. Well, it's going to be the position at time equal 0 plus the integral from 0 to 5. And we can see by looking at our calculator that these values match exactly. Now, total distance traveled is a little bit different. Total distance traveled doesn't involve just a straight integral, but because we know that during this portion of the curve we're going to be getting movement in the negative direction, or our net change is negative. During this section, we're going to get positive direction. What we really need to do is find out where is that value A? Where's that place where the motion changes direction? And then when we know that, we can say, well, how much travel happened while we went from 0 to A v of t dt? Well, let's see if we can do that. Let me switch over to our calculator. Here's the function, the velocity function already mapped out. Doesn't quite match the graph that we saw before, so let's change our Windows settings so that t is varying from 0 to 5. Okay, that looks a little better, but again, we're losing a bit of the graph. Let's now do a zoom fit, which will make all of the vertical values fit, and that looks like the function as it was graphed out for us. We want to find out what that value A is. Where is that place where we have the 0? So I'm going to go menu, and I want to analyze that graph, and I want to find that 0. Let's set a lower bound and upper bound, and it says, oh, it looks like it's 1 1/4. Now that may not be enough precision for us. So let me hover over that number and press the 1 button a few times. Oh yeah, we can see that's definitely not exactly 1 1/4. We're going to want that value to do our integration. Let's do that by setting it aside and putting it into a variable. Second stow. Oops, sorry, got ahead of myself. I want to click on that number first, then do a control stow, and then let's press the variable A. Say, all right, that's where that number is stored. And now, if I go over into another calculator window, I can actually do the calculation. We wanted to find out what is that integral from 0 to A, and because I put the velocity into the grapher, I can just refer to that value as f of 1, and we can go ahead and say f1 of t dt, and we find that the particle moved negative 3.79 during that time. We can also find out what did it do for that second amount of time as it went from A to 5 of f1 of t dt, and it went some 38 units, and so if we want to find the total distance traveled, we can take this value, and of course we got a negative value for the second one, so let's subtract that negative value so we get a net positive value, and we get 42.587 for our final AP compatible answer. Let me switch this over a little bit so we can see both of these at the same time. So we're going to note that that position, this was, oops, negative 3.793, and we'll want some more digits of accuracy, 443, that the integral from A to 5 of v of t dt was 38.793443, and that the total distance traveled is the sum, negative for that portion, positive for that portion, totaling up to a final answer that we can deal with, which is 42.587. Now, little trick here, we can also have found that number in a slightly easier way. Instead of finding the 0 and making sure we get the negative, we could also have done this. We could have said, you know, it's going to be the integral from 0 0.5, but in this case it would have been of the absolute value of the velocity, which again we said we stored in f1 of t dt. And you'll see that, oops, don't know what's going on there. Oh, did I lose something? Sure did. Let's try that one more time. I'm going to go from 0 to 5, and again I want this to be the absolute value of f1 of t. Get rid of this. That should work, and there we go. We see we get the same answer. Let's go on to another kind of idea. Let's summarize first of all this idea that we know that velocity, if we take its antiderivative, we get position. But let's acknowledge that this expression is a representative of the displacement for the antiderivative of the integrand. This also has another term. It's called net change, and we'll see that in a second. Recall that doesn't strictly hold for just velocity and position relationships, but rather also holds for any relationship where we have a rate of change as our integrand, that this expression represents that net change. Lastly, our typical rewrite of the second of the fundamental theorem of calculus part 2, you can see that we start at some initial position. Okay, I'm having trouble with my pen here. Let's try that again. Oops. Initial position and the net change, and when we add that together we get our final position or final value. Alright, so let's put those ideas together and for another couple of problems. So here's a problem. We were told about not the velocity of the car, but rather we're told about the acceleration. We're told that the acceleration is 2.4 t. Well, we'd like to know how fast the car is going 6 or 8 seconds later, so we can think of that velocity, that final velocity, being an initial velocity plus the net change in velocity, which we think of as the antiderivative of the acceleration. Plugging in what we know, v of 0 is 5. The antiderivative of 2.4 t is 2.4 over 2 times t squared. Plugging in our beginning and ending values, and with knowing that it's zeroing out at the bottom end, we get 81.8 miles per hour. Maybe more particularly, what we got was the initial velocity, which was in miles per hour. And this thing here is, funnily enough, it's in miles per hour per second multiplied by seconds, and those seconds cancel. So our ending unit is miles per hour. More generally, wait, why is it miles per hour per second? Well, because the acceleration was in miles per hour per second, and when we multiply by dt, that's in seconds. So that's why this particular unit is so strange. In general, we could say that we could find the velocity for any time t, and that's going to be initial velocity plus the integral from 0 to t of 2.4 u du, putting in a dummy variable there so that we can say that this is a function of t. So in general, we find that this equation describes the velocity at any particular time, but we're still going to note that t is measured in seconds. That's going to play a role as we try to find out how far the car went during those 8 seconds. So we can think of now that we have a velocity equation, that we've got an initial position plus a velocity being integrated with respect to time. There we go. We can take the antiderivative of 5 plus 1.2 t squared and get 5t plus 1.2 t cubed over 3 as we vary from 0 to 8. And of course that's 40 plus 0.4 times this really big number. Multiply that out and we get 244.8. But what unit is that in it? Does it seem reasonable that the car went 244.8 miles in 8 seconds? That doesn't seem very reasonable. That's because that unit is actually in miles per second, seconds per hour. Now, how is that again possible? Well, let's recall that this expression is in miles per hour. dt is in seconds. So here's our miles per hour, and multiply that by seconds. Now that's not a very usual unit, so we should probably do some conversion to get this to make some more sense. Let's take those 244.8 miles seconds per hour, and then if we multiply that by a value that's equal to 1, which is 1 hour is the same as 3,600 seconds, our hours cancel, our seconds cancel, and we get, we went about 7/100ths of a mile, and that value makes a little bit more sense. Okay, here's our last example for this particular part of the lecture. We're going to say, okay, well, let's say we know that the rate of potato consumption in a particular country was 2.2 times 1.1 to the t bushels per year, and where t is being measured in years since the beginning of 1970. How many bushels were consumed from the beginning of 72 to the end of 73? Well, we've got to figure out what that means. Well, when was the beginning of 72? Well, the beginning of 72 would be when t is equal to 2, if we follow this forward. When is the end of 73? Well, the end of 73 and the beginning of 74 are about the same thing. So we could say really what we're talking about is integrating that from 2 to 4. So what we have here is an integral that's going to represent the net change in potato consumption. Our value can be found by using our calculator, and in using our calculator we can see that we're going to get 7.06603, and that will be in what unit? Well, again, this part is in millions of bushels per year. The dt, we integrated in years. Those years cancel. We get 7.066 millions of bushels. And that concludes this part 1 of our lecture.